Okay. So, good afternoon, everybody. It's really a pleasure this afternoon to have here Gianluca Demartini. He is an associate professor at the University of Queensland at Brisbane. He has received multiple awards for his research in artificial intelligence and information retrieval. He is a long-standing and well-known member of our community. He has published more than 200 publications in major venues in computer science, and obviously this includes ACM CBIR and all the representative venues for our team. He is an ACM senior member and ACM distinguished speaker, and he is also a TEDx speaker. So a little bit of more of engaging kind of thing than just technical stuff. It's really a pleasure this afternoon to have a talk by Gianluca on humans or AI. Why not both? It's really up to date in this period and in these days. So thank you very much for coming and for giving the talk.
Thank you, Nicola, and good afternoon, everyone. So as Nicola mentioned, my background is in information retrieval. So let me tell you a bit where I'm coming from. My background is in computer science, and I've been building information retrieval access for a very long time. And then about 10 years ago, we started to look at how to involve humans in the loop in the development of these human AI systems. And while doing that, we realized the challenges of having human intelligence combined together with artificial intelligence. And we focused on questions around quality and efficiency of human annotations that are then used to train artificial intelligence systems. And more recently, we started to look at the impact of data and data quality on the development of machine learning systems, as well as with the applications for public good. For example, in the annotation and identification of misinformation, which I will give you some examples today as well. So that's the plan a bit for the talk. I will mainly be talking about recent publications that my group has been publishing in 2024. And there are more or less two parts in this talk. In the first part, I will focus on more the technical machine learning contribution. And in the second part, we look at the role of human intelligence in the development of machine learning models. All right, so let's start to talk about the development of machine learning models. And I will give you two examples. One is looking at active learning, so efficiently using human annotations and examples to train machine learning models. And the second example is on fairness of machine learning models. So if we think of supervised machine learning classifiers, what we note is requires is labeled training data, and this training data is usually labeled or annotated by human, usually experts. And when these expert annotations and the time experts need to allocate to label training data becomes expensive, we want to optimize and minimize the number of examples we need to build these models. So active learning is trying to do this and try to learn a model by annotating few examples, learning, and then based on that model, decide what to annotate next so that you can annotate the most useful examples. Usually active learning approaches look at diversity, so you want to select a set of examples that are diverse among themselves, but also representative of the population of the training data or the datasets, so that with just a few annotations, you can learn about the training example. So in this paper, what we did is we proposed a new active learning model that tries to both select a set of training examples to label, which is diverse and representative of the training dataset. And the way we did it is by using noisy labels. So the idea is you have two machine learning models, one trained with expert labels, and then you use this primary model or target model to classify automatically unlabeled training examples that you have not yet labeled. And this will give you what we call noisy labels. So there are some predictions made by the classifier of a likely label of the unlabeled training data. And with these noisy labels, you train a second model, which will be another supervised machine learning classifier. So we have these two models now, the primary model trained with expert labels and the peer model trained with labels generated by the primary. And then what we do with these models is we use these two models and compare their decisions to decide what to manually label next. And again, without going into the mathematical details, the intuition here is that we look at the decisions of these two models, and if these two models in a way do not agree on a classification decision, then we say that that example on which they disagree is a good one for a human expert to label, because from that example, the target model may actually learn the most. Instead, if the two models agree, then there is little information and little value in labeling that training example as with an expert. So again, two models, the target model, which is trained with expert labels, this generates noisy labels for unlabeled training data. These labels are used to generate, to train a peer model, and then we classify training, the class of training instances with the two models. If they disagree, we select those in an active learning setting to manually label next. And we see whether this gives us an advantage on learning speed. And that's what you see in these plots. On the x-axis, you have the amount of training data that you use to train the target model. And on the y-axis, you have the performance of the model. The approach I just described is the red line, and the other are baseline active learning models. And you see that eventually they all, in a way, reach a good performance. But what's interesting is how quickly these models increase their accuracy, which means you just need a few hundreds of training examples for the model to learn at a reasonable level. Then, of course, the more training examples you have, the better performance you have. But in a context in which the resources, the annotation resources are constrained, you want to select the instances that are most useful for the model to learn. And that's what we achieve with these models and by comparing their classification decisions. Okay, so this was the first example in which we have two models, one trained with the classification decision made by the first, and then we compare those to select what to label next. Now I'll talk about a second example in which the solution is very similar. We have two models, but the problem we are addressing is a different one. So here we are looking at fairness of machine learning model. For example, you have a data set like this one, which is a very popular data set to study fairness in machine learning. Here you have offenders, and your class that you're trying to predict is this one, which is a binary class that tells you whether the offender who has already offended will re-offend within 2 years of their first offense. And then we have a ground truth label, so this person has re-offended after 2 years, and this person didn't re-offend after 2 years. In this data set, you also have sensitive attributes, for example, gender or race. And for regulations or for other choices, we may want to develop models without using these sensitive attributes, right? We don't want to, for a model to decide whether someone will commit a crime in the future based on race attributes, for example. So what you do, you drop these attributes, and then you try to predict your class using the supervised model. And you want two things here. You want high effectiveness. You want that the classification, the prediction accuracy is high, but you also want the errors which are made, even if just a few, not to be systematically focusing on a subset of the population. For example, if your overall accuracy is 80%, you don't want the accuracy on the subset of instances with race equal white to be 90%, and the accuracy on the subset black to be 70%. The average will still be 80%, but it would be much better if you have a uniform, like a balanced distribution of 80% across all subsets of the population. And that's what we are aiming for when we try to increase the fairness of the model. So let me show you first an observation of what's the problem on this dataset, but we have also looked at other datasets in this paper, but I'll just work with this dataset as an example. So if you take this dataset and you try to predict the recidivism and you train a logistic regression model, what you see is a fairness issue. So what you see in these plots is the performance of this logistic regression classifier over two subsets of the datasets, the privileged and not privileged, by varying the confidence of the model. So you see here on the y-axis, you have different ways to measure effectiveness, and on the x-axis, you have a confidence threshold of the model. So you see that when the confidence is low, the difference between the two groups is very small. But then when the confidence gap increases, you have a wide gap between the effectiveness of the model on the two groups, for example, black, white, or male, female, and so on. So that's the thing we want to avoid, right? A big gap between the two groups. We are much more happy when the gap is very small. So based on this observation that the confidence of the model has a significant impact on the difference in performances between groups, we then developed an approach which is similar from an architectural point of view to the previous one. So what we do is a bit like before. We use our training data, we run a logistic regression classifier, and from this we use the confidence score of the model to split the data set into two and to train two different models with the two different datasets. So we have a high confidence subset dataset, and then we train a high confidence model with that. And we have then a low confidence dataset subset, with which we train a low confidence model. And then we have these two models. The high confidence one is also trained with the ground truth labels from the dataset. But with this model, we generate pseudo labels or noisy labels like before, which we feed to the low confidence one. So the assumption, the intuition behind this is that by doing this reinforcement training loop, we are trying to align the two models and therefore align the performances and therefore reduce the gap between subsets of the population. Again, without going into the mathematical details, let me just give you the intuition of what we are doing. In a space, in a multidimensional space, a classifier would be a decision boundary. And then our two groups are the low confidence and the high confidence. In a space, the points which are classified with low confidence are the ones close to the decision boundary. While the points classified with high confidence are usually those far from the decision boundary. So we have these two classifiers, the ones trained with this and the ones trained with that, and then we learn one model from the other. So fundamentally what we are doing over iterations, we are moving this decision boundary in between these two groups in order to, in a way, balance the classification errors made between the two groups, the two subsets of the population. So to give you an idea on whether this works, again, this is just one example. You find more in the paper, but the approach I described doesn't really, is not really different in terms of accuracy, classification accuracy compared to baseline models, but it has a significant gain in fairness. So here we have two different fairness measures, equalized odds, that looks at how the true positive rates and the false negative rates is different across these privileged and not privileged groups. So we want them to be as equal as possible. So the lower this number, the better. And demographic parity, again, looks at how classification decisions are not dependent on sensitive attributes such as race. So in summary, using these two models trained with different subsets of the trained data, we are able to maintain a similar level of effectiveness, but increasing the level of fairness of the classifier. All right, so these were two examples of machine learning models that were focusing on optimizing the use of human annotations in an active learning setting and optimizing the fairness of the model in the classification decisions being made. Now, we have seen two examples of how a machine learning model can, in a way, learn from humans and potentially replace human decisions automatically. Now, the question we should ask ourselves is whether we should actually replace people with a machine learning model to take decisions, for example, in the Compass dataset, right? Do we really want an AI to predict whether someone will reoffend, commit a crime in the future, and maybe we preemptively put them in jail? Should we do that or not? So that's, in a way, the next question to look at. And so what we are seeing in the talk so far, but in general, is a lot of research focus on how and when large language models and AI system can replace people in tasks. And there are many examples in which this works really well. Another example is relevance judgment. Microsoft Bing is now replacing human assessors with GPT-4 to generate relevance judgments to train ranking models for Bing, and this works really well. Now, on the other hand, you could have, this is the model replacing humans, and here so far we talked about humans generating examples for machine learning. Sorry, there is a lot of attention on these models replacing humans, and I will give you one example next. But what I believe is really interesting is what's in between, right? You don't just have, should this be done by people, should this be done by an AI, but what happens when they actually work together? And there is a full continuum in between, right? If you take the middle point, on one side you have a human in charge using an AI as a copilot, but still the human is completing the task. And on the other side, you have an AI in charge, but still with human supervision, for example, providing feedback or double checking some difficult cases. And there are all sorts of equilibrium balances in this spectrum. So we'll try to explore a bit this spectrum and see what happens when humans and AI actually work together. But before we go in the middle, let me give you one example of what happens when you have AI completely replacing humans. So the example we are looking here is advertisements. Traditionally, online advertisement is what fuels the internet economy, maybe the world economy. And traditionally, how you do online advertisement is you use human experts like designers who design and craft an ad, and then you make use of social media to micro-target and send these ads to the right people. For example, you can decide that you want to show this ad to someone who owns an iPhone and goes running Saturday, and you will micro-target a very small set of people on social media, but still what you need is to design this ad by yourself, right? With the creative, with an actor if it's a video. Now the question we are asking here, can large language models generate persuasive content as well as creative human designers can? So to answer that question, we set up a user study in which we have 4 conditions. We have 4 different advertisements, 2 generated by human experts, by designers, and 2 generated by a large language model. And 2 of these 4 are targeted for a personality trait known as openness, and 2 of them are generated for or created by a human for a personality trait known as neuroticism, which are at the end of the spectrum. So the study we did is we had 4 conditions with these 4 ads. We present one of these 4 ads to a subject that arrives to our study, and we ask them questions like, would you buy this product, or would you click on this ad? So and they are only exposed to one of these 4, so we have 4 different groups. After this one ad, we show them all 4, and we ask which of these 4 would you prefer or would you click on? And only at the end, we have a big 5 questionnaire so we can measure the personality traits of the participants, and we can check whether the ad we showed at the beginning was a match for them or not. So after we run the study, we can make a few observations and comparisons. One comparison we can make is whether an ad that matches your personality performs better than an advertisement that does not match your personality, right? So we were not able to micro-target, but we were able to measure the personality of our participants, and a posteriori we can check whether the ad we served them was a match. But more interestingly, we can compare the performance of human-generated ads as compared to ads generated by the large language model. So what we see here is that ads that are matching a personality perform better than those that do not match a personality. No surprise there. What is maybe more surprising is that there is no statistical significant difference in the performance of the human-generated ads compared to the large language model-generated ads. To reinforce that observation, remember in the second step, we showed them 4 ads and we asked them which one do you prefer. And here the winner is the human-written ad targeted to the openness trait, followed by the 2 AI-generated ads, and last we have the human-generated ad for the neuroticism trait. So from this we see that overall the ads generated written for openness are the best performing ones, and this seems to be already known in the literature because again, when you walk around, you see billboards, they are designed to target the openness trait. So that's the type of ads we are used to. But again, when we want to compare humans and AI, what we see is no clear winner, right? Because you have human here, and the AI generated ads in the middle. So again, no clear winner like in the statistical significant test before. So the observation here is that humans are not anymore better than AI in creating persuasive content. And this is very concerning in my opinion, because remember what I told you before, social media gives us the ability to micro-target, but now large language models gives us the ability to generate personalized, persuasive content at scale. And then you micro-target this. So every single one of us could get an ad created customly for them and then presented to them in a micro-targeted way. That doesn't sound really a nice future to me. So that's why maybe we do not really want AI to fully replace people. And again, then maybe what's better is having them work together to complete the task. So that was my hypothesis, right? Maybe we don't just want people to do it or an AI to do it, but maybe if they do it together, it's better. So in the rest of this talk, I will try to explore this setting, also known as model in the loop, in which we have a human in charge completing a task, but they get AI assistance in a way, which is a bit what happens with our students on our daily life. We use an AI assistant to write emails, to summarize long documents, to generate exams, to answer exams. So we use these AI assistant tools a lot. So let me talk about two studies we did in which we tested what happens when you have this type of AI assistance, specifically in a human annotation scenario. So we've been using, as I mentioned at the beginning, crowdsourcing as a way to build human-in-the-loop systems. And over the years, we have seen three things about crowdsourcing. Crowd workers apparently can be relied upon to assess misinformation. Misinformation assessment is typically a task completed by expert fact-checkers who follow a forensic process. So you would assume that a non-expert crowd workers would not be able to reliably assess whether something is fake news or not. But it boils down that in the right setting, with the right setup of the task, you can actually get high-quality misinformation annotation back from the crowd. The second thing we know, and I'll talk about next, is that there is a bandwagon effect. If you tell a crowd worker that other people think this is fake news, they will also say this is fake news. And the third thing we know is that crowd workers started to make use of large language models like ChatGPT in the completion of their tasks. For example, relevant judgments or misinformation assessment. Now, I'll tell you a bit about these, the last two things, and then we really want to ask the question, what happens when they make use of an LLM? And for that, I will talk about a control study in which we make them use a large language model, and we see how they their annotations change. Okay, but first, let me tell you, before we look at the AI, let me tell you what happens when crowd workers are exposed to other crowd workers' decisions. So this is our standard misinformation assessment task. Let me go through it. What we show these human annotators is usually a statement made by a politician, here in box number 2, and then we ask them for a judgment. We ask them whether that statement is true, false, or in between. And then we also ask them for a justification of their judgment. We ask them why they think that statement may be false. So in this study, what we did is we added this box number 3, and we played with it in different conditions. So in some control conditions, this box number 3 was not there, so just statement, judgment, justification. And in the other conditions, we are showing them links to web pages that have been provided by other crowd workers as a justification for their judgment for exactly this statement. So we have shown these statements in previous studies to other people, and we ask them, give us a link to a web page that supports your judgments on whether this statement is false or true. And now we feed this back to these new participants. And we feed them back in different ways. We just give them a link with no information, or we sort these links by how many other crowd workers have reported this link. We show them the domain, for example, CNN.com. We show them the title of the web page we are linking to, or we tell them a bit about who the other workers are. For example, this link has been reported by 5 other Republicans. And we see what happens in these different conditions. What we ask our current participants to do is to obviously judge the truthfulness of this statement, but before they do that is to check this evidence and then come back and tell us whether this evidence was useful or not useful for their judgment. So the first thing we noticed when we ran the study is that not all of them follow our instruction. And some of them actually would report a link to be useful with a thumbs up without ever looking at it. So they never click on the link, because we can log whether they click and open the page or not. And some they never click, but they still report things as useful or not. And that's, again, not surprising. Many crowd workers would try to very quickly finish the task to complete and get the money. But what's interesting is to compare this behavior across conditions. So we call adopters that follow the instructions. They at least open the link, they go to that web page, they come back, and then they report whether a link was useful or not. And we call non-compliance those that give feedback on the links without ever opening the links. And interestingly, we see that the condition in which there is most non-compliance is the order one. So the condition in which we order the links telling them the first one at the top is the one that others have reported the most. And this is a classic bandwagon effect, where you see people following the majority. If others have said that's useful a lot, or that's the most useful, they will go with it and they will say that's the most useful without even looking at it. So that's a finding that was observed already in the past, and we also observe here. The other thing we notice is that the evidence we provide is not necessarily good. So here on the y-axis, you have the quality of the annotations provided by our participants, and here you have the different conditions. So you see that the best quality is actually achieved when we don't give any link to external web pages. And then all the others perform worse. So this, in a way, means that the evidence we give them, and actually that other crowd workers have reported as evidence, is not necessarily useful to reach an accurate conclusion on the truthfulness, but may actually mislead them and bias them in the wrong direction. And finally, what we observe is a political bias that we have observed in previous studies as well. So here you see, for the condition where we tell them 5 other Democrats have reported this link as useful, a strong correlation between the current participants' political background. So what this means is that if I'm a participant that self-reported to vote Democrats, and I tell them that 5 other Democrats find this link useful, they will jump on it without necessarily looking at it. And the same is true for the opposite, right? If you voted Republican and I tell you 7 other Republicans found this useful, then you have a much more desire to find that useful. Again, all these observations are not really surprising in a way, but they are a bit concerning, right? Because really, we are not now tapping into the individual mind and knowledge. Rather, we have all these different type of bias which are affecting and introducing noise into the labels that we are collecting with crowdsourcing. So that's the first issue. Now, second issue that happened very recently is the use of tools like ChatGPT in crowdsourcing tasks. So in this work that we presented 2 weeks ago at ICWSM, we ran a survey, a questionnaire on 3 different crowdsourcing platforms: Mechanical Turk, Clickworkers, and Prolific, over 2 points in time in May and December last year. And we asked them, do you actually use tools like ChatGPT to do crowdsourcing tasks without being asked to do so? And scarily, especially on Mechanical Turk, the vast majority of crowd workers said yes. So up to 80% of crowd workers make use of AI assistance tools like ChatGPT to complete crowdsourcing tasks. And again, this is very worrying, right? Because we are not anymore tapping into this collective intelligence that crowdsourcing platform used to give us. All this has become is an API to ChatGPT. So why do we go to a platform like Mechanical Turk? We should just go directly to an OpenAI API to get the answer from there, like Microsoft Bing is doing. So should we do that or not? Let's see. So we know that this happens, right? We know from this observation is that many crowd workers use tools like ChatGPT to do their crowdsourcing tasks. So let's see what happens when they do. This is the same setup as before, misinformation assessment. We show a statement made by a politician. We ask them true, false, or not, or in between. A justification. And in this case, we also ask a confidence level, like how sure you are that this statement is false. But now we play with this AI assistance condition. So we either go the control without the green box, or we tell these crowd workers, an AI has looked at this statement and thinks this statement is false or is true. And even we give them a natural language explanation why the AI thinks that statement is true. So we have these 4 conditions, the control without AI suggestion, and 3 conditions in which we have an AI classification label, an explanation, or both. These AI conditions were generated with GPT 3.5, and each participant did 6 of these statements in a task. So let's look at what happens when they use this type of tools. So first, quality. Interestingly, if you look at the quality of the labels, there is no statistical significant difference between conditions. So having an AI as an assistant doesn't necessarily decrease or increase the quality of the labels. However, what's interesting is that neither of them, the humans or AI, is perfect. And if you just look at the AI, so these are the correct classification decisions. Here and here you have the wrong decisions. You have a strong presence of overestimation of truthfulness. So GPT 3.5 tends to say that the statement by a politician is true more than it should. So it's very generous in saying something is true. And what happens when the crowd workers are exposed to the AI recommendation is that they also tend to overestimate truthfulness as compared to when it's not. So again, they make a similar amount of mistake, but when the humans are exposed to the AI, they make similar mistakes than the one the AI is making. First, concerning observation. So next, we looked at the confidence reported by the crowd workers. And also, like for quality, there is no statistical significant effect of the presence of the AI on how confident crowd workers are. However, there is an interesting, useful signal, which is this one, which is how much labels agree with the ground truth based on correlation with confidence. So the more confident crowd workers are, the more they agree with the ground truth when they are exposed to the AI. And this is positive, right? Because we generally don't have the ground truth. We need to trust the crowd workers. And if we can use their self-reported confidence as the signal on whether their label is good or not, that's good. And it seems that when they are exposed to an AI, so the classification plus the explanation, they tend to self-assess their accuracy better. So they know if the label they provided is good or not. So that's a positive result. We also looked more, based on the previous result on quality and overestimation, on reliance and trust in the AI assistant. So generally, like before, we see that crowd workers tend to be more critical towards truthfulness of this politician as compared to when they are exposed to an AI. So when they are exposed to an AI, they become more generous, overestimating truthfulness. But we also look at reliance. So here we look at how the agreement between humans and AI. And we see that when they are exposed to an AI, these three boxes, the agreement between humans and AI is higher. So the decision taken by the AI and the final decision taken by the human in charge tends to be more aligned with the AI when they are exposed to it. Again, not very surprising, right? If they don't see the AI, they take different decisions. When they see an AI, they follow the AI recommendation. So this is a sign of reliance, right? They rely on this AI, and they rely on this AI a bit too much because the AI tends to be over positive, and also they become over positive. So that's a problem inside, right? There is a over reliance in the AI. And finally, the other observation is that they are doing 6 of these judgments in sequence, and the first one they do really matters. So the first one they do, depending on the randomization of the order, could be one in which the AI is giving a correct recommendation or a wrong recommendation of the label. And we see that when the first recommendation is accurate, the yellow box, leads to higher trust in the system as compared to when the first recommendation is wrong. So the first time they are exposed to the AI classification, if that classification decision is correct, then they think, oh, this AI is really good, and they always use it. If the first time they are exposed to it, the AI is wrong, then they are less willing to trust the AI for the remaining tasks. And finally, we look at 2 things, how quickly they do the judgments. And we see that when there is an AI assistance, they are faster, which is good for them because they can do more tasks and get more money. Again, remember, with a similar level of accuracy. The other interesting thing we noticed is the following. So I didn't talk about this, but on the right side, you see they have a search box here. And ideally, that's available for them to use to find evidence online about their decision they need to make about that statement and about whether that statement is true or not. So we looked at how much they use this search box in the different conditions. And what we notice is that people who are not exposed to the AI assistant tend to use the search engine much more. So when you have the AI telling you the statement is true, then they don't search online for additional evidence as much, they just rely on this AI. But if the AI is not there, they start to look on the web much more. For example, they copy-paste the statement and they look for evidence online. Also, interestingly, we noticed that those who search more above than the median of number of queries in the study, they tend to diverge more from the AI, right? So those who search the web less, they rely on the AI more. Those who search more, they make a different decision from the AI. Again, an interesting signal on how some people are over-reliant while others tend to be more critical and looking for more evidence to support their own decision. So to summarize, what we observe here is that AI assistants, when they work in collaboration with humans, is that it's useful for efficiency purposes, right? It makes people faster, they make decisions faster, they need to look for less evidence, so they can annotate more in the same amount of time. However, we also observed over and over again this over-reliance in the AI, right? And this leads to bias labels. So in this example, it was an overestimation of truthfulness, but it could be political bias if they follow other people's labels. Again, there is this strong over-reliance, which is problematic because what we really want is their own opinion, their own judgment, not the AI judgment, not others' judgment. So what does this leave us with? I think it's more questions than answers. I think we have seen in this talk that human data is critical to train AI, to make AI fair and safe. We need human labels, but these human labels are biased, and there is nothing really we can do about it. We can just embrace this bias, measure it, and then finally surface it in these models to the end users for them to make a judgment on how to adjust for this possible bias. I think it's unavoidable to have this bias in one way or another, either from humans or from AI. It's there, and we are not yet able to really measure it. We've seen that AI and large language models can replace humans in many tasks, but should they really replace humans in all these tasks or not? Should they work together? We look at also when they work together, it's not really ideal, right? We have this over-reliance in the AI, which is not the best of the two worlds. It's a bit the average of the two worlds, which is not what we expected either. So I don't know. I really don't have an answer for you today. I think my questions next are how we can make humans and generative AI systems, build them in a way that they can get the best out of human intelligence and artificial intelligence rather than washing out the ability of both. But I don't know how to do it. Thank you very much.
Thank you very much, Gianluca, for the very interesting talk. Any questions, guys? I have one. I mean, what you describe is a little bit what everybody is asking themselves about how we position ourselves, etc. You provided grounded experiments in this, but apart from where to position or what is the implication of the different degrees, is this more a technical problem or more a policy normative problem? Because, okay, we have evidence, but how we control things or how we ensure that when things happen, how we expect?
Yeah, good question. I think we need the regulation of AI, but we need it in a way that doesn't stop people to do the things they want to do, and doesn't. So I don't think the solution is to restrict the applications of AI. I think the solution is to empower people to be aware of what are the risks and the limitations of using AI, and then an informed end user will make hopefully the right use of it, as long as there is a positive intent, right? There is no, we don't want mistakes that happen because of lack of knowledge and information about the risks. Obviously, there is also malicious use of AI, and that needs a different kind of approach to it. But for general applications for good, I think we need to empower the users to understand the potential, the opportunities, but also the limitations, rather than saying, let's not use AI in medicine because the risks are high, which is, again, a risk that could happen with the wrong type of regulation in place. So to answer your question, I think it is also a technical challenge. It's not just a policy decision. It is a technical question on how we empower users to know about these models and build these models in a way they are more transparent, and tell people, don't trust me too much, or in this case, or again, build models in a way they can work together with people. At this point, we don't have that yet, I think. I think it's too much of a, as we have seen, an over-reliance. These models are so good, whatever they say is good. People use generative models if they were retrieval systems, but they are just making natural language up. Yeah. So I think that's the problem, but the solution is information literacy, is not policy.
Thank you. Any Carlo?
Okay, it was very nice talk, and thanks for the. I'd like to have a comment from you about education, computer science, with respect to all these new scenario. In the sense that we are used to educate, to start class students, high-level technical students, from the kind of traditional way thinking about the procedure, object orientation, so on and so on. Here we are in a different world. So this is it is already time for switching the education paradigm, or it's better to wait for a while?
Yeah, good point. I think we need to train the next generation computer scientists differently. What I tell my first year students in computer science at UQ is that we are going to give them superpowers, and it's up to them to decide whether to use them for good or for not, but they're really going to learn superpowers, right? They can be things that are extremely powerful, extremely dangerous, and it's up to them to how they're going to use them. They can cure cancer, or they can destroy democracies. So to answer your question, I think, yes, it's our responsibility to train the next generation to be responsible, right? We cannot just give them the tool to build these things and let them go. It's our responsibility to teach them how to build things in a safe manner. It's like in civil engineering, right? We teach them to build bridges, but we teach them to build bridges that are safe for people to go over, and they don't put lives at risk. I think when we train people to build AI, we need to train them not to put people's life at risk in the same way.
I have a question. It's not related to one point that you were explaining in terms of how much the LLMs were being over confident in telling that all the statements were true. So my question was actually two. First one is how much they were saying is almost to 100%, or it is more like a let's say more balanced amount of overconfidence in a sense. And the second one is what happens? Are they saying false, or are they just being evasive in answering you? Because from my personal experience in this last month, I'm trying to use that to answer me on the correctness of facts in a knowledge base, and either they tell me everything is true, or they don't know, but they don't want to tell me, even if I try to force them with 1,000 prompts, that something is false. So I think it's quite similar in sense of wondering if you have any kind of opinion or say scenario on this.
No, so we had a very similar experience, right, with this convincence of models telling you what you want them to tell you. I think, I mean, to answer your question, there are multiple elements, right? On the one hand, you have prompt engineering. So if you have the right prompt, you can get reasonably quality labels, and labels for most of the cases you're asking a label for. But yeah, we had this issue of being over positive on classification decisions. But again, once you measure metrics of quality, they are reasonably good. They are not all the time or randomly distributed. So on the other hand, the thing to pay a lot of attention to is what is called, I never remember the name, poisoning, I think, data poisoning. So a model having seen your data set during pre-training, and therefore knowing the ground truth labels because they have seen it in the pre-training, right? So if we use open data sets which are online, there is a high risk that this data set has been seen by the model before. And when you ask them, is this relevant? Is this true? Is this blue? They will know it because they've seen it before. And that's not the experimental setting we want, right? That's a mistake in the experimental setting. However, today it's very difficult to avoid because we have no idea what's in the pre-training, because all these models are put there, open source and available, anyone can use them. We don't know how they have been built. And that's a problem. That's a problem because, again, all these experiments may be in a way affected by these by these issues. So I don't know how to do it, but I agree there is a bit of a problem. The third answer to your question, I think, is that this problem also comes from the reinforcement learning with human feedback element of it, in which they make the model become very conservative and very low risk taking type of model. This happens in the pairwise judgments that are given for the type of output the model generates. So those are the 2 points in the model creation process that are an issue, right? The pre-training, which is not transparent, and the pairwise judgments of the output, how the output should look like, which is not, it's again, it's one size fits all, right? In some cases, it's very good not to have harmful content generated, but on the other, when you want a decisive label, it's not a good way to train the model. So I think we need different models for different purposes. So far, we just have this one model does everything, which is not ideal.
Questions? I have another one. When you have shown the joint work between humans and AI and how they reciprocally, not reciprocally, but how humans were influenced by further level it, and the fact that maybe they use, I mean, in your experiment, it was controlled, but you may have crowd workers or fact checkers doing exactly that without telling. Again, how do you control and detect this? Because if you have data, how can you tell how they have been produced? Is there a risk to get into a kind of recursion? I need another AI to check the data and tear apart.
Yeah. So I think there is an answer to your question. I think there could be a technical way to check, but I think that's not the question. I think we should give up completely on the idea of controlling and stopping the use of AI, even in crowd work. I think, again, very quickly, the more we go on, the more these AI are embedded in Microsoft Word and our email client. And everything we do is not anymore human generated. It's a collaborative effort between human and AI. So I think it's a lost cause to enforce not using AI. But I know I understand why we like not, and I talk about this for an hour. Why we don't want them to use AI, but I don't think it's possible, right? Because it's how content is going to be created from now on. It's going to be a collaboration between humans and AI. So we need to accept that and deal with that.
Yeah, I understand, and I can share these view, but the point is, if we know, as it happens from your experiments, that these kind of collaboration introduces some specific kind of biases, etc., we may still want to compensate for those biases. Otherwise, loops and loops will reinforce them. So if I cannot tell how data have been created, either I always assume they are biased in this way, and maybe I overestimate, or I may still need some way to understand what's going on. Not for preventing, but
yeah, just to measure. Sure. Yeah, I think we can assume that. Again, what to do with it, it's not an easy question, right? You could adjust. Imagine you know that they've been using that ChatGPT model, and you know that the model overestimates by 20%, so you adjust by 20%. But even that adjustment is a choice made by you or whoever is collecting the data. And that's their own bias, right? Someone else would say, well, that collaboration is actually representative of how people think, because everyone is using that model and therefore everyone is over generous. So should we adjust it or not? I think it's a really difficult question on how to adjust. And I don't think we should, because any adjustment decision will introduce the bias of whoever decides. And this is typically a 20 years old male software engineer in North California, which is not necessarily representing everyone else in the decision of how to adjust, right? So I think the better way forward is increasing transparency and empowering end users to adjust by themselves, right? If they think, I don't know, there were 80% Democrats in the people who annotated data to train this model, then I'm not happy and I want to adjust it. But first, we need to give this information, to transparently surface this information to people, because at the moment we are not at the adjusting, we have absolutely no idea about what these models are built and who annotated the data. So I think that's step number one. Once that is transparently surfaced, then we empower everyone to adjust differently how they want. I don't think one adjustment is the best for everyone.
Okay, if this is your plan, you will need also a lot of information literacy in between, because even if you may to surface these, then people need to understand.
Yeah, I agree. People might not
giving
be
a car with so many pedals and knobs.
Yeah, I think we need to design systems that are enabling this adjustment, right, for everyone. Again, it's very difficult, and I think there is a lot of work to be done, but that's the future I see, where people are empowered, but we need to support them. And what we can do is build systems that are easy to use and helpful for them to adjust, but we need to empower them, and it's our job to build systems that are empowered.
Any other questions, curiosities? Okay, so let's start.
Thank you very much. Thank you.